Hi, my name is Madison Burns, and today I'm going to be talking about standing waves on a string. So first, I'm going to give a short introduction on waves. So right here is what we call the amplitude. Right here is going to be the trough, and that is the lowest maximum point. And then right here, the highest maximum point is a crest. And then one wavelength can either be from a crest to a crest, a trough to a trough, whatever's easiest. And when I'm talking about the standing waves on the string, which is what I'm really going to be focusing on here, we're going to be talking about a transverse wave. Is where the wave is going to oscillate perpendicular to the direction of the wave path. So if this was the wave direction, then this wave is going to oscillate like this. So it's going to be oscillating up and down, while the wave is going to the right, which then they're going to be perpendicular to each other. So waves can also interfere with each other. So if one wave is going this way and the other is going this way and their crests and troughs line up with each other, then you will get constructive interference, and the crests and troughs will add up to make a wave like this. And then there can also be destructive interference, is where the crests line up with the trough, and a trough ends up with a crest, and then you get destructive interference where they subtract from each other, like so. So when I'm really talking about standing waves on a string, I'm talking about when a wave will interfere in a steady way in order to create this, what is called a standing wave. So in a standing wave, there's going to be points that are stationary, and these are called nodes, as you can see here. So on this is a node and this is a node. And then antinodes will be the maximum amplitude points, and they're going to be the parts actually oscillating. So that would be like here. And for the standing wave on a string, since the two ends of the string are fixed, these must be nodes. And there are an infinite number of standing wave patterns that are possible, and these are characterized by the harmonic number, which is called n. And generally, we consider the first harmonic the fundamental, and that is going to be n equals 1. And this occurs when exactly half of the wavelength fits in the string. And while like n equals 2, a full wavelength fits in the string, and so on. So the formula generally used to figure out the wavelength for a certain harmonic is going to be wavelength equals 2 divided by n times L. And L is the part of the string that is vibrating, like so. So now if we want to relate the velocity of the wave with the wavelength and the frequency, we're going to use the formula V equals wavelength F. And so this really helps determine the sounds that you were hearing, and generally lower frequencies will lead to like what we consider like deeper and like more bass sounds, while higher frequencies will lead to more high-pitched sounds. And these sounds kind of occur because when a string is plucked, the disturbance will travel along the string, and how fast it travels really depends on multiple things. So we're going to look at the formula V equals force of tension divided by mu for this. So really, the force of tension within the string and the mass density, which is this right here, mu, are really important in determining how fast the string is going to travel and propagate. So the mass density is generally the kilograms per meter, so it's really just how much mass per unit of length on the string. And all of this kind of goes into how fast the wave is traveling, and thus the frequency and the tone of sound you're going to hear for each harmonic and for each string. In order to demonstrate what I talked about in the introduction video, I decided to make a shoebox guitar. And to do this, I cut a hole in the shoebox to replicate what a guitar would be like. And then I will need 2 rubber bands, which I have here, and one is just a lot thicker and one is a lot smaller. And then I have 2 pencils, and these are going to act as the fixed endpoints of the strings, or the rubber bands in this video. And then I have a ruler, which I will need to measure the length of the rubber band and the length that is going to vibrate on the guitar for future calculations. And then I also have a scale right here, which I will need to weigh the rubber band. So first, I'm going to take the measurements I need to do mass density calculations. So I need the mass and the length of the rubber band. So I'm going to place this rubber band on the scale. It says 4 grams. Let's try again, as it said -2 on there. Now it says 5. There we go. So next I'm going to measure the rubber band. This is the best way I can do it, and I'm using the centimeter part of the ruler. So I have 23.3 centimeters. So the total length of the rubber band will be double that as I have it folded, so it'll be 46.6 centimeters. So now I'm going to move on and put this on the shoebox. Gonna make sure it's all even here. Okay, so there we have one, and I'm going to place this other smaller rubber band on here as well, just to demonstrate the sound difference between the 2 rubber bands. But it's not heavy enough to mass it because the scale, it just won't register on the scale. So let's get this on here. So now we have the 2 rubber bands on the shoebox. Next, I'm going to place the 2 pencils to act as the fixed endpoints. So I want them to be about 20 centimeters apart just to make my calculations easier. So I'm going to place them in here and then use this ruler. And I'm measuring from the inside of the pencils here. So there we got about 20 centimeters. So now we have the shoebox with the rubber bands and the pencils on. So this is the finished guitar. So now I'm going to show you what it sounds like. So here we have the thicker, if you can hear that. It's a much lower tone. Then we're going to do the other string, much higher pitched. So, as I explained in the introduction, this has to do with a lot with the mass of the strings. And this one is a lot heavier as it registers on the scale, while this one does not register at all. So, now I'm going to move on to the calculations portion. So, my goal now is to try to calculate the force of tension needed for my red rubber band to create an 82 hertz frequency, which is generally the fundamental frequency of the 6th string of the guitar. So that's a low E note. So I'm going to use the formulas 2L over N equals wavelength. I'm also going to use V equals wavelength times frequency. And then I'm also going to use velocity equals the square root of the force of tension over mu, which is the mass density. So first, I'm going to use my length calculation, which, as I showed in the video, is 20 centimeters, which is the part of the string actually vibrating, so between the 2 pencils. And this was 0.2 meters. Next, I'm going to write down what I got for the mass density, and for that I did the mass that I found, which was 5 grams, which is 0.005 kilograms, And then I'm going to divide that by the length of the entire rubber band that I found, which was 23.3 centimeters for half of the rubber band. So total, it was 46.6 centimeters, which, if you convert to meters, is 0.466 meters. So if you calculate that, you will get 0.0107 kilograms per meter as the mass density of the red rubber band. So, first I'm going to use this formula here. And I'm trying to calculate what my string or my rubber band here would need to have for a force of tension in order to get a fundamental frequency of 82 hertz. So if it's a fundamental frequency, we're going to be using n equals 1. So I'm going to use this formula, and with my numbers that I have, so I'm going to take 2 times 0.2 meters, and then I'm going to divide that by 1 as I'm focusing on the fundamental frequency, or the fundamental harmonic. And when you do that, you get 0.4 meters. Next, I'm going to use that wavelength calculation and plug it in to this. So if I do that, I'm going to have V equals 0.4 meters, and then I'm going to use the frequency that I'm focusing on, which is 82 hertz. So if I plug that into my calculator here, we will get 32.8 meters per second. So that's going to be the velocity of the wave. So next, I'm going to plug that right into this equation. So if I do that, I'm going to have 32.8 meters per second equals square root of force of tension divided by my mu calculation, which is right there. So I'm going to divide it by 0.0107 kilograms per meter. So we want force of tension by itself. So to do that, I'm going to square both sides. If I plug that into my calculator, I get 1,075.84 equals force of tension divided by 0.0107 kilograms per meter. And this over here is going to be meters squared seconds squared. So now I'm going to times both sides by 0.0107. And if I do that, let's see what I get. I get 11.5 newtons for the force of tension. So this is the force of tension that I would need if I wanted to create a fundamental frequency of 82 hertz on the shoebox guitar using the red rubber band.